Hello, welcome to a series of podcasts on the topic of LLMs. I'm here talking with Sohrob Kazerounian. Sohrob and I have these long drawn-out one-on-one conversations. You'll get a glimpse into how some of those go in these sessions. There will likely be 5 to 6 of these sessions. This first podcast will be the prehistory of LLMs. So ultimately, if you're not interested in the prehistory of LLMs, if you want to just fast forward to a world in which LLMs already exist, you can go to the second session. But if you are interested in the more kind of philosophical underpinnings, this session is for you. Sohrob, you and I talked before this, and we decided the prehistory, rather than beginning at the point when mammals come out of the primordial ooze, we decided to begin slightly later with Bertrand Russell.
Yeah, so sadly, we don't have the time to talk about the primordial ooze onward, but yeah, so a sensible starting point on a lot of this is really when philosophy takes what's referred to as the linguistic turn, right? And that basically is a point at which philosophers start really focusing on language users. When people are talking, how are they referring to things in the world? What are those things? What if they don't exist? And Russell is a sort of good point of departure for analyzing what some of that means. So Bertrand Russell, logician, mathematician, one of the things he ends up getting really sort of focused on is what happens when we say certain types of sentences or propositions, right? And a famous sort of proposition that he really analyzed pretty deeply was the present king of France is bald, right? This should either be true or false, right? Mathematicians like neatness, compactness, things should either be true or false, and this is a simple enough statement that should be easy, right? But it's clearly not true, right? There's no present king of France that's bald, but the opposite is also not clearly the case, right? It's not the case that the present king of France is not bald, right? It's,
but there is no present king of France.
But there's no present king of France, right? Ultimately. But how does that, natural language description map onto this more sort of formal, logically expressible proposition that then you can evaluate, right? And so Russell's solution to that one is effectively to say that when you say things like that, really what you're saying is that there's an X such that if X is the present king of France, and for any other thing Y that is the present king of France, then Y must be X. Then therefore, if X is the present king of France for any X, it must be bald, right? Mm-hmm. Now you can reject the first of those claims. There is an X such that X is the present king of France, and we can say the thing is false without necessarily falling into these traps, right?
So it sounds at that point like you're talking almost like what we think of as computer languages, right? It's like if, then, else, etc., right? And so how does that take us from Russell to Turing?
Yeah, so essentially this question of formalization of statements, right? It's related to basically what Turing and his project is basically that, can we formalize the notion of computation, right? And even our phrase or referring to things as a computer, really what Turing was doing was describing what a human computer, one who computes, would do when they're in the process of doing some, for example, math, right? There's a step-by-step sequence of things that you're doing, and Turing wanted to really formalize what that process was, right? What Turing ends up proposing as a means of doing that is what we now refer to as the Turing Machine, a universal computer that any algorithm must be expressible as a Turing Machine, and essentially you get the birth of computation by this attempt to formalize some of the notions we have around not just logic, but inspired by its relation to how we talk about things at a natural language level, right?
So how do we get from there, which is obviously a slightly different, a very different departure to kind of neural nets and the initial conception of kind of a neural net?
Yeah, so you have now a computer, right? And so at some point in the same sort of time span, you have numerous people working on cybernetics, artificial intelligence pops up. But amazingly, the first neural network is proposed very shortly after Turing proposed this idea of a computer, Turing machine. And it's proposed by these two researchers, Warren McCulloch, who's this, freewheeling, whiskey-loving, poetry, producing, just autodidact, very smart guy. But he ends up basically meeting up with this another self-taught, basically genius, Walter Pitts, right? And Walter Pitts, essentially, as a child, like starts reading Bertrand Russell, Principia Mathematica, really getting involved in sort of like, self-teaching all of the things he can about logic and mathematics. And the two of them, when meeting up, basically end up, designing a project where they want to be able to say, out of, if we were to try and explain how the brain is producing logical statements or evaluating them, can we create networks of neurons that can evaluate these propositional, logical, sort of calculus types of statements, right? And what they end up developing is the first neural network. It doesn't adapt on its own, and there's a number of issues, but it's amazing because it's only 1943. But they proposed a neural network that can do basically logic. And amazingly, that neural network itself ends up inspiring John von Neumann and the von Neumann architecture and the move from just the Turing machine in theory to the computer in practice. And one other interesting tidbit there is that actually urban legend has it that Walter Pitts was the inspiration for Good Will Hunting, because as a kid, he was he was raised in an abusive family, ends up spending all his time in the library, running away from home, going to see Bertrand Russell give lectures, and then being sort of found as a genius who then gets brought to MIT and involved in all these projects, essentially.
So this chapter kind of this session kind of ends with Turing then in the 1950s. So tell me a little bit about, and this is obviously something we've all heard of. So what did Turing do in the 1950s?
Yeah, so now we have this idea of mind and machine sort of melding. Mm-hmm. And Turing writes an article essentially asking, can machines think, right? How would we even know? Is the question even meaningful? Like, what does it ultimately mean for a machine to think, and so on? Turing's proposal is to say that actually, I personally think that the question is meaningless, but let's propose a way of actually testing or at least talking about this, right? And so Turing proposes the Turing Test, which is to say that, like, if I'm conversing with, let's say, a computer or a human behind a door I can't see, can the computer fool me into thinking that it's human? Yeah. The imitation game, inspired by, apparently people didn't have much to do at the time, but that was a parlor game that people would play, and a useful sort of conceptual hook for thinking about machines and thinking in general.
A modern reinvention of the mechanical Turk.
Right? Exactly. Yeah.
All right. So let's go from there to, I think after that, there was this stage that we went through where people tried to explain how humans learn. So talk a little bit about the behaviorists, about Chomsky and some of that.
Yeah. So as all of these sort of revolutions are happening in the, you have the computer being proposed, the first neural network, and so on. The prevalent sort of current in psychology at the time was what's referred to as behaviorism, which tried to treat the brain as a black box. Let's not think about it. All we need to worry about is input output. You can think of Pavlov's dogs, for example, right? There's just the sort of, you present a dog with some food, it salivates. You ring a bell at the same time as presenting it with the food. Now we can shape its behavior. We don't need to worry about what is structurally going on in the brain when all of this is happening. And so there's a behaviorist take on how language is acquired. And Noam Chomsky comes along in the 50s and says, no. the behaviorist position on let's ignore the brain, language is acquired as a means of just this, the environment, is a stimulus that induces a response and so on and so on, and then you get this chain of language coming out. This is not how any of this happens. So Chomsky writes a scathing review of a famous behaviorist book called Verbal Behavior. It's Behaviors with B.F. Skinner. Destroys the field with that review. Like really does some serious damage. But essentially at the same time is proposing what becomes formal linguistics, right? Chomsky's position is that a number of things. First, that there must be some sort of universal grammar, right? That there's simply not enough, children are not exposed to enough data, enough evidence of language to be able to infer what the correct grammar should be for their language, right? This is actually an argument referred to as the poverty of the stimulus argument, right? So there's just not enough data for kids to do all the things you'd have to do to actually learn a language or a grammar. So therefore, there must be a universal grammar.
So it's an interesting split now that you get, right? It's like computers, it's hard for computers to mimic how humans learn. So now you start kind of seeing potentially this bifurcation between how do we teach computers, and it's not just how to try and mimic how humans learn, because humans have these innately complex linguistic structures that with a relatively small number of samples they can be trained by. But we can't really, we struggle to recreate that in computers. So talk a little bit about what happens from here in terms of n-grams and other techniques.
Yeah, so when we talk about LLMs, the LM in that stands for language model, right? And the language model really is sort of inspired by this idea of like, actually, maybe the statistics about the language itself are enough to learn something about its structure, to be able to understand its semantics, some of its syntax, and so on. Right? And the first attempt at doing that is roughly to say, let's count up how many times a word occurs. And actually, interestingly here, this is kind of what happens with cryptanalysis and the thing that like Turing was doing between proposing the Turing machine and then talking about whether or not machines can think. But basically, you count up the probability or the frequency of various words. You can start to map out whether or not sentences are likely, unlikely, grammatical, ungrammatical, and you can think of this as a, the way it's proposed is by doing n-grams, right? If your n is equal to 1, you have a unigram model, which is to say that let's just count up the frequency of all words, right? Obviously, the words that are most frequent are going to be things like the, a, and so on and so on. But if you're just using the unigram probability, there's very little you could capture about the language itself, right? Take a sentence, for example, like the cat in the, right? Every part of your being wants to say cat, right? Cat is going to come next. And the reason is because, that's both. Exactly. Yeah, it's in the data, right?
Yeah.
But a unigram model would say the next word should be the next likely. You only have the count of each individual word. The next likeliest word should be whatever the most prevalent word in English is. That doesn't feel right, right? Like that doesn't capture it. So a bigram model moves to n equals 2, which says let's count all pairs. Let's see how frequently each of the pairs occurs, and then build a slightly more statistically valid.
And so try and 4-gram and so on. And so you can go deeper and deeper, right? And so you can remember longer and longer structures, but then it also becomes more and more complicated, and the amount of memory in which you would need to store this becomes kind of blows up, right?
Yeah, exactly. So you can kind of capture things that are like a trigram model, 4 grams, whatever. You'll be able to do things like the cat in the hat, right? But as you really want to start to capture long-range dependencies, not even that long, but like, just standard sentence length dependencies.
From a sentence that has 8 words in it, where the 8th word really depends on, to give meaning to the first 2 words. It's like, yeah, you need to span. Yep. And so that's the problem, is you don't have enough overlapping plates to connect yourself, to connect that to meaning.
And
so So we have that, and then so the challenge there then becomes, I would say, coming out of that is like, how can we express these complex relationships in a more compact, computationally affordable way, right? So this is kind of where we get the return of neural networks.
Yeah. So the neural network sort of thing is that like it shows promise and then dies out for a while and shows promise again and then dies out for a while. So in the 80s, it returns with a fevered pitch, and basically people are like, hey, we can use these neural networks to model aspects of the language, right? They're using it to explain things about child language acquisition, but also even things like, let's see if we can replace these n-gram models, right, with linguistic models that actually capture something about the probabilities of the word-to-word transitions that essentially sidesteps the problems that you get with n-grams as you get to larger and larger n, right? And so obviously there's something useful in the statistics of n-gram models that for speech recognition, language modeling, machine translation, but if you can't scale, it's no good. The interesting thing in the 80s is you have this group of researchers who are really convinced that neural networks, because the brain's doing it somehow. So let's create these neural networks that also, at a hand wavy level, mimic that process, and we should be able to do something that's functional, right? So you get researchers like Jeff Hinton, Jan LeCun, and numerous others who are famous for reintroducing neural networks. Hinton actually recently himself resigned from Google over fears about the speed and sort of lack of regulation around AI and large language models and how these things are being developed and so on. So his concerns there are interesting to see
are on the record,
now.
obviously, that people can read out. So okay, so that brings us to close kind of to the end here. So we have these things called LSTMs come along. Talk a little bit about those, and then we'll transition kind of to the next session from here.
Yeah, so the neural networks that were being used in the 80s, they had some deficiencies. They had, even though they in principle could capture these long-range dependencies, had their own issues. LSTMs are proposed by a researcher, and essentially they are really good at learning. They're really good at capturing these long-range dependencies, still kind of being run on toy problems at the point of their introduction in 1997. By 2010, they're starting to really actually show some interesting capabilities. They're being used for speech recognition and starting to finally beat these more statistically grounded models and systems. They're being used for generating handwriting models of cursive and so on and so on. And so people are like, wait, these things are actually starting to become functional. Trained on, at the time, a large data set of Wikipedia text, for example. At the time, 100 megabytes was a large data set, right?
Yeah.
And so you'd have these character by character models that were starting to reproduce really interesting, sort of at a superficial level, but interesting because like the things before
things that could sound like a Wikipedia article.
Yeah, and even actually with the markup language included and so on and so on, right? And so
I mean, we use LSTMs as well, right? As in that time window, we have been kind of using them for some of our problems.
Yeah, so actually they're great for time series models, right? Sequential data, and essentially like we have taken it and run it on iSession data and used it for a classification system, used it for a variety of different types of understanding something about the sequence of iSession data. In almost exactly the same as the language model does, except instead of characters, it's bytes sent, bytes received, and so on. Now the amazing thing here is that in the 2010s, these start to get really. I think Bloomberg actually even referred to LSTM as like the most commercially viable neural network ever. But in 2017, you have the introduction of transformers, and these are essentially ways to scale LSTM models up to a size that probably would have been very difficult to and very expensive to do with LSTMs, just because they're parallelizable. They don't have these recurrent connections that mean you have to do things in sequential order. And these transformer models essentially it's introduced by Google, but companies like OpenAI essentially make a gamble. They have this belief that scale it up, feed it enough data, and these models won't just be doing the expected sort of text completion that you're training the model to do, but they'll actually start to exhibit some interesting emergent properties and intelligent behavior. And yeah, it's a bold gamble.
This hinting at the current era that we find ourselves in.
Yeah.
Cool. Thanks a lot for this initial session. As we said, this is the prehistory. Next session will be LLMs, and more LLMs, and some follow-on sessions from there. Thanks again, and we hope that you actually watched this session, so you have the grounding, and we will see you soon in the next one.
Thanks all.